That's what your forums are for. Did Lucy leave? She left all her money. I'll put it right there in case she comes back in for it. Okay, people.
Lucas, hurry up.
All right, Jedi, so we got to start. Yeah. All right, let's roll with it. I think we got most everybody situated. All right, so electron configuration and counting atoms. Today is lesson 5, which means we are halfway through our first quarter. Yay! You've made it an eighth of the way through the year. Congratulations. Oh, moving along. It's also the last lesson of unit 2 today. So Jordan, how about right there? There you go. Yeah, right there. That's a spot. You're looking for a spot? Okay. Find a spot, any spot. I don't care. All right. So being that it's the last lesson of unit 2, that means you can expect what this week? A test. Everybody knows that, right? Okay. Don't worry. I'll show you your study topics. Okay, so we're going to start with electron configuration. Now, how many of you read this and were like, blah, 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 like, yeah, there was a lot of stuff in this last lesson. We're going to start with our buddy, Professor Dave, right? We love, this is Professor Dave with the long hair. We know if you've known Professor Dave for any length of time, he gets short hair at some point. Everybody's disappointed because we like long-haired Professor Dave. He also never fully buttons his shirts, if you haven't noticed that about Professor Dave. Yeah, there you go.
I would like to add somebody comment on a team that I think Jack may show because Professor Dave said that.
We love Professor Dave. Yeah. So anyway, so we're going to talk about Pauli exclusion principle. Still going to be a little blah, blah, blah by the end of it, but then I'm going to break it down for you and show you exactly how much of this I expect you to know for this class, because you can get really in depth with this. Okie doke. So let's start with our buddy Professor Dave, if he wants to go. And we're gonna get commercials now, even though they're embedded. I've tried. I don't like them, but I can't go away. Go away.
Let's talk about quantum.
Oh boy.
Now that we understand that electrons are both particles and waves, we are ready to.
What are you doing? Dave. Oh no, he's still talking over here. Hold on. Oh no. Hang on. Shh. Alexa, turn on Media Center. I don't know why I did that, but we'll fix it. Maybe. Can you tell we've been watching Yellowstone? Alexa, turn on Media Center. Yeah, it's a little weird. It could be anything. Here we go. All right.
To learn about how electrons are arranged in an atom. The location and energy of every electron in an atom is determined by a set of 4 quantum numbers that where an electron can be found. There are S, D, P, and F orbitals with different shapes, and they look like this. Remember, these shapes are not electrons, just regions in space where electrons can be, and each one can hold up to 2 electrons. The more electrons an atom has, the more of these orbitals it will need to accommodate them all. The first quantum number is the principal quantum number n, which can have any positive integer value. We saw this when we learned about the Bohr model. It represents the energy level of the electron. Each orbital will have an n value, and the larger the value of n, the further away from the nucleus it is. The next quantum number is the angular momentum quantum number, L. This can have any value from 0 to n minus 1. For example, if an electron has an n value of 3, it can have an L value of either 0, 1, or 2, because 2 is 3 minus 1. The L value describes the shape of the orbital. When L equals 0, we are describing s orbitals, which are spherical. Just one of these per energy level. When L equals 1, we are describing p orbitals, which are lobes that extend outwards on 3 axes. There are 3 of these per energy level. When L equals 2, we are describing d orbitals, which are weird looking, 5 of these per energy level. And when L equals 3, we get f orbitals, which are even weirder looking, 7 per energy level. Next, we have the magnetic quantum number, m sub L. This can have a value of anywhere from negative L to L. So if L is 2, m sub L can be negative 2, negative 1, 0, 1, or 2. This quantum number determines how many orbitals there are of a type per energy level, and therefore describes a specific orbital amongst a particular set. When L is 0, m sub L must also be 0, and that's why there's only one f orbital per energy level. When L is 1, m sub L can have 3 values, which is why there are 3 p orbitals per energy level. An L value of 2 gives us 5 values for m sub L and 5 d orbitals, and an L value of 3 gives us the 7 f orbitals. The last quantum number is an easy one. It's the spin quantum number, m sub x. This one will be either 1/2 or negative 1/2, no matter what. So every electron in an atom has a unique set of quantum numbers. No 2 electrons in an atom can have precisely the same 4 quantum numbers, as is stated by the Pauli exclusion principle.
Oh,
This is because any orbital can only hold up to 2 electrons, and even the 2 electrons in the same exact orbital will have opposite spin values. So let's try to describe different sets of quantum numbers and what they mean. When n equals 1, L must be 0, and m sub L must also be 0. That means we are describing the 1s orbital. It can accommodate 2 electrons, which will have spins of ½ and negative 1/2 respectively. This is the lowest energy orbital, so any atom on the periodic table will fill this orbital first. The electrons in hydrogen and helium occupy this orbital since they have only 1 and 2 electrons respectively. When n equals 2, L could be 0, which would give us the 2s orbital, or L could be
oh,
SDA.
Oh, no, no more of this. We don't know why this keeps happening. Yeah, but-
P1, meaning m sub L.
Usually when they're embedded, the commercials don't come, but for some reason now they are.
P orbit. The outermost electron in the second row of the periodic table will occupy these orbitals. When n equals 3, L could be 0, giving us the 3s orbital. L could be 1, giving us the 3p orbital, or L could be 2, giving us the 3p orbital. A large atom will have to use all of these orbitals and more to house all of its electrons. The Aufbau principle tells us the order in which an atom will fill up its orbitals. This is determined by their relative energy. Orbitals that are further away from the nucleus have higher potential energy, so it'll be 1s first, then 2s, then 2p, 3s, 3p, and so forth. We can use this to determine the electron configuration of any atom. For example, a neutral chlorine atom has 17 electrons. So looking at the orbitals, each of which can hold 2 electrons, let's fill them up starting at the lowest energy and then climb upwards. The 1s orbital gets 2 electrons, one spin up, the other spin down. Then the 2s, then the 2p's, then the 3s, and the last 5 will go in these 3p orbitals. Hund's rule says that for electrons of the same energy, you put 1 electron in each orbital first before doubling them up. So 1, 2, 3, 4, and 5 gives us a total of 17 electrons for chlorine. That means chlorine has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5.
Right.
The numbers before the letters are the n value for the orbital. The numbers after the letters tell you how many electrons sit in each type of orbital. If you want a quicker way to determine electron configurations, just know which areas of the periodic table correspond to which types of orbitals. This area is called the S block. This is the P block. Here's the D block, and then the F block. When we are determining the electron configuration for an atom of a given element, the easiest way to do it is just travel left to right and up to down on the table until you get to the element, since each element has one more electron than the last. Looking at chlorine again, the top row is just the 1s orbital, that's full, so 1s2. Going to the second row, where n equals 2, we fill the 2s orbital, which holds 2 electrons, hence 2 elements. The 2p orbital, which holds 6, so we pass 6 elements. Then the next row down, we fill the 3s orbital. And lastly, we get to the 3p's and count 1, 2, 3, 4, 5. 3p, 5. A common abbreviation is to use the noble gas from the row above and list it in brackets. This would be read as neon core, and it implies the ground state electron configuration of neon. Then you just list the valence electrons of the element, or the ones that correspond to the row it is in. We can use orbital diagrams to visually depict how the orbitals are filled, and they look like this. Don't forget Hund's rule. Fill each set halfway before doubling up. For a quick definition, atoms with unpaired electrons in their orbital diagrams are called paramagnetic and are attracted by a magnetic field. Atoms with all of their electrons paired are diamagnetic and are not affected by a magnetic field. So to summarize, N tells us the energy level, L tells us what type of orbital, M sub L tells us which specific orbital amongst a set, and N sub S tells us the spin. Each electron in an atom has a unique set of quantum numbers, and an atom will fill up orbitals with electrons according to the Aufbau principle until all of its electrons have a place to stay. This is a tricky concept, so if you feel confused, try watching one more time from the top. Otherwise, let's check comprehension.
Anybody want to give it a shot?
No.
No.
No? Nobody wants to even give it a shot?
Listen to music.
Random.
You like the marimba?
I've heard many words, none of them make sense.
Don't worry.
Second one.
We're gonna clarify.
It's second one.
There you go. It's a little bossa nova or whatever it is. All right, so that's clear as mud, right? Everybody's like, oh, that was so easy. I understand now. Oh, you don't? Okay, don't worry. This is how I expect you to be right now. Is this about how you're feeling? Yeah, which one of these memes is you? Find one that's you. Which one represents you?
I don't want to be strong.
The dog.
I have no clue.
The lady with no dentures. I don't know. What? Who knows who the guy in the flat is? Nobody. No, that's John Ritter from Three's Company. Okay. Even Post Malone is confused, y'all. He's like,
I
what?
don't know.
All right. So, no worries. I'm going to tell you what out of that I expect you to know and understand. So this is quantum mechanics. It's not easy. It's the reason why there aren't a whole ton of quantum physicists and whatnot hanging around, right? Because it's really difficult stuff. So the quantum model describes what when it comes to locating an atom at any place? What is it? It's describing, Colin. The probability, exactly. It's describing the probability of locating an electron at any particular place. So when we talked about Schrodinger and Heisenberg having the quantum model as being the commonly accepted model, passing by the Rutherford and Bohr models, which are those little solar style models, right? Solar system style models. It's giving you a probability. It's not saying that electron is in all those places at once. It's saying it's likely to be found in one of those places. So each electron is assigned what quantum numbers? Do we know? You know, Colin?
4.
4. There you go. All right. So we're dealing with 4 quantum numbers. 2 electrons of any atom can have, no 2 electrons of any atom can have the same 4 quantum numbers. That quantum number is specific to those electrons. Each electron has its own quantum number, which is what he was showing you, right? He was saying this one, we're going to categorize this by this, by this, by that. Okay, so the electron configuration of an atom reveals the number of electrons an atom has. All right, so what do we remember from Professor Dave here? N is what? What does N give you? Caitlin, do you remember?
Like power.
Yeah. Energy level. I see where you're going. You're right. Energy level. How far from the nucleus is this electron? And what does L give you, Jordan?
What type of orbit?
There you go. It's an orbit type. Exactly. Very good. All right. And then what did M sub L give? Yusuf?
The exact orbital.
Exact orbital. Very good. All right. And then what was N sub F, Liam? The spin. Okay. So what do you suppose is meant by the spin? What does it mean by that?
Curveball or a speed.
Yeah, kind of, yeah, pretty much. Like those electrons are which direction is it going? Is it going this way? Is it going this way? How is it spinning? You know, they are moving like opposite one another, each two, right? Because they have the same charge. So they can't be moving together, right? Because they're repelling each other. All right, now here's what so that's what you need to know. You need to know that. See where it says for this class, here's what you need to focus on. What does that mean? Okay, now off bow. So off bow, an electron occupies orbitals in order from what kind of energy to what kind of energy? What are we doing? Where are we going? From what to what? James? From low to high, right? So we're going, it's like climbing a ladder. So off-bow principle basically says that your first electron is in your lowest energy level, and then they get higher as they go, which means that these guys here that have very few electrons don't have that many energy shells, right? Not that many energy levels because they don't have very many electrons. But when you get down to these guys down here, they're further and further, those electrons get further and further away from the nucleus, which means they have more and more energy. Now, when you heated up your chemicals in lab today, you cause those electrons to get excited and to move up and kind of shift a bit. And then when they settle back down where they belong, they release that energy they gained from moving up. They release the energy they gained from moving up as colored light. So that's what you saw, right? Okay. Here's what you need to know about Pauli's exclusion principle. No two electrons in the same atom can have identical values for all four of their quantum numbers. So in other words, no two electrons can occupy the same what? BJ?
Spot.
Yeah, the same orbital, the same position, right? And two electrons in the same orbital have to have opposite spins. There you go. All right, so that's what we're looking at. Everybody following so far?
Yeah.
Okay. Now, Hund's rule. Here's what I need you to know about Hund's rule. Every orbital in a sublevel is what occupied before it is doubly occupied? Yusuf?
Fully occupied?
Not fully.
Half.
Half or singly occupied. So you have two electrons in each of these orbitals, right? When you're filling out your electron diagram, you fill one out for each orbital at that energy level before you fill out the second. Remember how he had the little arrows pointing up and then he went back and put the arrows pointing down. All of the electrons in singly occupied orbitals have the same what? Spin to maximize their total spin. Okay, so you've got maybe like, remember when he did chlorine, he had 3 there that were all going up. They all have the same spin. So when you fill out your diagram, you up arrow, up arrow, up arrow, then down arrow, because he needed 5 in that level. That's what he was going for there. You remember it. I don't know. So here's the blocks. Remember he said know your blocks? Okay, here's how the blocks work. So if you know your blocks, that helps you know where you are when you're writing out an electron diagram. Yeah?
Is it going to appear on any tests or anything?
You may be asked to write electron configurations for certain things, okay? You'll have time to practice, don't worry. All right, so now orbital diagrams. These are where you see the little off-bow principle in action, okay? Hopefully we won't get a commercial, no promises. I can't get rid of them and they're making me insane. No,
Same one.
maybe when the election's over, we'll stop getting these because they were never a thing before for embedded videos.
Are a visual representation of where the electrons are in an atom. we're going to include energy levels, sublevels, and orbitals in this representation. Now, if you think back to the video on Bohr's diagram only will show us the energy levels. And so the orbital diagram is going to give us a little bit more information as to where those electrons are. To draw the orbital diagram, you have to follow some rules, and there's 3 of them. We'll talk about each one of these rules, and then we'll try drawing some orbital diagrams. Here's our first rule, the Aufbau principle. And the Aufbau principle states that electrons will fill the lowest energy orbital first. Again, this is the lowest energy orbital, not the lowest energy level. I've listed all the sublevels for the first 5 energy levels here. You can see here's n equals 1 and 2 and so on all the way down. Now this isn't as simple as just following along and saying, well, here's the first energy level, we'll fill that first, then fill the second, then fill the third, and so on. There's actually a little more to it. We're not going to get into exactly why this is in this video, but we'll at least learn this method of figuring out which is the lowest energy orbital. And here's what we do. We write this grid here, and you can see I have all the S's in a column, all the P's in a column, all the D's in a column. And then we draw these arrows at a 45-degree angle. As you can imagine, this is almost like a grid here. Drawing these arrows through at 45. And then this is actually going to tell us the order of the orbitals as we fill them. And so we start here at the first arrow, and we follow that arrow along. And the first thing we encounter there is the 1s, and that's the lowest energy orbital. Once we get to the finish here, and once we get to the end, we go back up to the next one. Follow that down, so the next lowest energy level, or sublevel here is the 2s. Then we move up, then we have 2p, 3s, go back up, 3p, and we think we should have the 3d next, but it's actually going to be the 4s. Then we go to the 3d, 3p, 5s, and so on. And so this is a way that we can look at and learn what that order is. So again, the Aufbau principle says electrons will go into the lowest energy orbital first. Let's go to our next rule here. It's called the Pauli exclusion principle. The Pauli exclusion principle is actually pretty simple. It just says that for every orbital, there could be a maximum of 2 electrons. So 2 electrons per orbital, that is the max. And you may remember, we've talked about this rule before, that they have to be having a different spin. So we'll have one with the up spin, we use these little half arrows here, one with a down spin. So that's the Pauli exclusion principle. And our final rule here is called Hund's rule. Another name for this is the empty bus seat rule. Okay, let me just first explain what we call the empty bus seat rule. Now just imagine taking some kind of public transit, a bus or a train or something like that. And you get onto that vehicle and you look and see all the rows of seats, and you see that all the seats are empty except for just one seat where there's somebody sitting right there. And so when you go to choose your seat, you're probably not going to sit right here next to that total stranger. I'd imagine you would choose a seat that's empty. And this is the way electrons view orbitals. If we can imagine that each one of these seats represents an orbital, if an electron sees an orbital has somebody in it already, even though orbitals can hold 2 electrons, if they see an electron's there already, they're not going to go there. They're going to find another empty orbital in the same energy level. All right, so that's Hund's rule. Let's go ahead and try drawing an orbital diagram here. Let's draw the orbital diagram for calcium. And if you look at calcium here on the periodic table, you can see that its atomic number there is 20. So it has 20 electrons in that atom. I've already set up this orbital diagram here, and let me just show you the different parts here. This is just one way to draw an orbital diagram. There's other ways to do this, but I've drawn this on a scale of increasing energy. So low energy is down here, the lowest energy, and the lowest possible energy is the 1s orbital. Now just remember, 20 electrons, that's what we have to account for. So let's start filling these in one by one, starting with the lowest energy first. We use these little half arrows to represent those electrons. So we have 2 in the 1s, 2 in the 2s, and then we'll fill 2p according to Hund's rule here. So the next electron is going to occupy an empty seat or orbital, and then we'll start pairing them up. So I've accounted for 10 electrons so far. Next we'll go to the 3s, and then we can go to the 3p following Hund's rule. And then finally, the 4s, and there's where the 20 electrons are gonna go. Let's try another one. Take a look at nitrogen on the periodic table. You'll see that nitrogen has 7 electrons because its atomic number is 7. So let's draw the orbital diagram for this one. So let's set it up, starting with that scale here for the energy level. And the very lowest possible energy is going to be the 1s. And so let's fill that up first.
1, 2, right? Up arrow,
So
down
put
arrow.
2 electrons into the 1s, so we have 2 of the 7. And then we'll go up to the 2s, put 2 electrons in there. And then what comes after the 2s, it's gonna be the 2p, and that has 3 orbitals. And we have 3 more electrons to put in there. And so following Hund's rule, those electrons are all gonna go into their own orbital, according to the empty bus rule.
All right,
Patreon, support me on Patreon.
support me. All right, so let's look real quick. Here's your Bohr diagram. You've seen this before, right? And this shows you your energy shells as first, second, third, right? Your energy level 1 can hold how many electrons?
That's it.
2. Your second energy level, 1, 2, 3, 4, 5, 6, 7, 8, right? Third, 18, right? See how they are there? All right, and then those same shells, we give those names. So we've got, you won't see K very often, but K, L, M, N, they've been named. I don't know why they start them with K, L, N, don't ask me. And then these are your S, P, D, F, right? We talked about how they were weird shapes. Remember, he kept saying weird. Professor Dave, he used the very scientific term weird shaped orbitals. Gotta love it, right? All right, so I want you to understand that you have energy levels. Each energy level can hold a certain number of electrons, and each of those energy levels has an orbital, and the orbitals hold how many? Right, there's 2, and there's different orbitals within different energy levels. All right, so let's have a look here at iron. There's iron. This is what matters, what's at the end. And the reason that matters is because this right here, this is what's doing your interacting with other atoms, okay? So all this stuff at the beginning is going to be the same. So where's iron? Right here. So manganese, which is right before iron, is going to be identical until it gets to that very last bit, right? So it's just going to continue to be the same, and then what you're adding on at the end is what really matters, because that's what's doing the interacting, because it's the electrons in the outermost energy level that matter. So you can see it right here. Sometimes you'll see this. Sometimes there will be a periodic table that actually has this little bit of information at the end. Not usually, but sometimes it's there. So what's it actually look like? So let's see. This is for iron, all right? Okay, 3d6, 4s2. Here we are. So in shell N, you got 2, and that's a spherical orbital with 2 electrons, one with an up spin, one with a down spin, right? But that's not all. Then you have 2s2, which is your L shell. That's shaped kind of spherically too. And again, it's another orbital, and it has 2 electrons, one with an up spin, one with a down spin. Then you have your 2p6. Well, what shape is that? Oh, that's this weird shape. This is this kind of barbell shape. Ah, yeah. So when you're looking, what does it actually look like? It's like layers upon layers. Then you get this other spherical one back on top, because that's an S again. Then here's your 3p6 coming in. There's another. See how it continues to build? So if you were to say, what does that iron atom actually look like? That's really what it would actually look like if you could visualize it. Yeah. Did you? What did I can't see it? What is it?
Female Iron Man.
Female Iron Man. Okay. Yeah, FE. There you go. So yeah, so this would be, if you could actually see the atom, it's not anything like that Bohr model. that just looks more like a solar system model. Actually, a quantum model would look more like this, but keep in mind, all these parts are moving, right? Nothing's still, everything's moving. The orbit, the barbell orbital itself is not going to stay in place. It's going to be doing this sort of thing. And then within it, the electrons are moving. So it's constantly in motion. And then whoop, and here we're almost to the end of it. Goodness sakes. Oh my goodness. So here we go. There's your iron. Is that at all what do you imagine when you see a Bohr model? Like, not, yeah, real? Uh-huh, yeah. And there you go. 26, right? 26. So that's actually how they'd be placed, where you'd find them. But wait, they can move, like I just said. So keep in mind that they're constantly shifting around, releasing energy, absorbing energy. When you heat them, that's what you saw today, right? You heated up those metal ions and those electrons jumped up some energy levels. When they jump back down, they released energy in the form of light. And that's how you got different wavelengths of light, different colors. So how do we count atoms? Okay, so we just talked about electron configurations. Now we're going to shift gears. How do we count atoms? All right, the masses of atoms are expressed in what? What is it, Colin? Yes, AMUs, atomic mass units. That's our unit. Okay, remember we have like, what's our metric unit for volume? PJ? No, PJ. Or liters typically is our unit, right? We got liters. What's our metric unit for length? Meter. Okay. See where we're going with this? How about for mass? Caden? Grams. Okay. That's what we're dealing with. So when we're measuring atoms, we express them in AMU, atomic mass units. That's for mass of an atom. We're not going to use kilogram for mass of an atom because that number would be crazy small, right? So the mass of an atom of carbon-12 isotope is defined as exactly 12 atomic mass units. The mole is the SI unit for the amount of a substance that contains as many particles as there are atoms in exactly how many grams of carbon-12? Yeah, okay. That people tend to be like, do what? All right. I don't know if anybody saw my fun shirt, but it's a little faded, but it says 2 moles per liter. We're going to be doing some moles in the next couple of weeks. So what the heck is a mole? Okay, we're going to explain what it is, but a lot of times people will call it a chemist's dozen. You know how you know that there are like a dozen cupcakes? There's 12 cupcakes, but you're counting them by the dozen. That's kind of the same thing. It's another term that means a predetermined quantity. So what's the number? It's called Avogadro's number, but there's an actual number. Does anybody know it? Yes. Okay. This is one to memorize, people. This is one to memorize. A lot of times it's not necessary to memorize like a quantity. Does anybody remember like the, what was the gravitational standard? Do you remember? Remember, James? Yeah, 9.8 meters per second squared. There's your, yeah, okay. So that's for acceleration of gravity. That's your gravitational standard. This is another one to remember. 6.02 times 10 to the 23rd particles per mole. Particles per mole. Particles can mean lots of different things, okay? 6.022 or 6.02 typically times 10 to the 23rd is what you're going for. So that's exactly what's on my shirt. So what's a mole? Okay. Here's where it gets fun. Hey, mole, where are you going? I have an identity issue. I need to find out who I am. All right. What is a mole? He doesn't know. He's going on a journey. So it's 6.02 times 10 to the 23rd atoms is a mole. 12 grams of carbon is what we're basing this on. All right. So the mole is a counting unit. It's abbreviated MOL, no E. That helped us a lot, right? We lost one letter of a 4-letter word. That's so helpful. Abbreviated MOL, and it is defined as the number equal to the number of carbon atoms in exactly 12 grams of pure carbon-12. So if you took 12 grams of carbon-12 and you were able to count the atoms, you would have 6.02 times 10 to the 23rd atoms in 12 grams of that particular substance, okay? It's called Avogadro's number. It honors his contributions to chemistry. We'll find out who he is in a minute. He's kind of fun, actually. So 1 mole of anything is 6.02 times 10 to the 23rd units of that substance. So just like a dozen eggs is 12 eggs, a mole of eggs is 6.02 times 10 to the 23rd eggs. Uh-huh.
Is that Snoopy, but a mole?
I think it's a mole that looks a little Charles Schultz-ish, but yeah. Lucas. Yeah. Grado. Oh no, that's not mine either. That's somebody else's typo, but I'm glad you caught that because I swiped that one. Somebody spelled that wrong. Avogadros. Okay, so look, mole problems. Actually, we do have mole problems on the side of the house right now. I'm gonna have to set the dog loose on some mole tunnels that we found next week. Doing what a dachshund does, right? Going to ground. So mole problems, call 602-1023, right? There's a million of these great little mole memes. They're fun. All right, so what's a mole? A mole is the amount of a substance that contains exactly 6.02 times 10 to the 23rd atoms, molecules, or ions. It's a counting unit, so it can mean any of those things, atoms, molecules, or ions. The number's Avogadro's number, like we said, and it's named after the Italian scientist Amedeo Avogadro, which was a suggestion put forth by a French scientist, Jean Perrin, to recognize Avogadro's work. Now that recognize is spelled the British way. I didn't write that either, but yeah. Okay, so we're honoring this guy when we come up with this number. So a mole is essentially that many of something in chemistry. So in 18 grams of water, in 55.9 grams of iron, in 32 grams of oxygen, and 58.4 grams of table salt, and 197 grams of gold, and in 4 grams of helium. All right, now, a mole is a different mass for different elements and compounds. So this seems confusing, but it's similar. Again, think about your dozen. A dozen elephants to a dozen mice. Although their masses may be different, you still have a dozen of each. So if you had, look back here, a mole of water would be 18 grams, but a mole of iron is 55.9 grams. Look at the difference between iron and oxygen. 55.9 grams to 32 grams. Why is oxygen less? It's nowhere near as dense. It's smaller. The whole atom is smaller. It's less dense, right? Okay. It's often referred to as a chemist's dozen. It's an easier way to count large numbers. So the number of moles equals the mass in grams divided by the mass of 1 mole. Ooh, don't worry. We'll be doing lots of these in lab. So here's how you convert moles, okay? We're going to get another Kamala Harris commercial. I just know it. Or maybe it's going to be a different one. There it is. I cannot make it stop, y'all. I think it is a Trump one. I don't even know.
Brought to you by In this video, we're going to learn how to do mole conversions for elements, how to calculate the molar mass of the compound, and how to do mole conversions for compounds. But before we jump into all that, you might be wondering, what is a mole? Well, there are lots of different moles in the world, but in chemistry, a mole is simply a large number of things. It's kind of like a dozen, only bigger. 1 dozen is 12 things. 1 mole is 6 times 10 to the 23rd things. That is 600 billion trillion things. Now that's a lot of things. But why is the mole such a big number? Because atoms are so small. Suppose you wanted to know how many hydrogen atoms are in 1 cup of water. If you were able to count all the atoms, you would find that there are about 15 trillion hydrogen atoms in a cup of water. But if we count using moles instead, that works out to be only 25 moles of hydrogen atoms. So we use moles to count atoms, molecules, and other chemicals. It turns out that there's an even better reason why 1 mole equals 6 times 10 to the 23rd things. And that is that 1 gram equals 6 times 10 to the 23rd atomic mass units. Let's see what that means for a particular element. Break out your periodic table and look for lithium. It's the 3rd element. On the bottom of the square, you should see the number 6.94. This is the atomic weight of lithium, but it is also the molar mass of lithium. So 1 lithium atom has an average mass of 6.94 AMU, and 1 mole of lithium atoms has a mass of 6.94 grams. That gives us a convenient way to count atoms by weighing them, and the molar mass is the conversion factor between grams and moles. Let's try a problem. How many moles of lithium are in 25 grams of lithium? This is a one-step unit conversion problem, and like any unit conversion problem, the first thing you should do is write down the quantity that you know. In this case, 25 grams of lithium. Next, multiply this by conversion factor fraction. Remember that for mole conversions, the molar mass is always a conversion factor. 1 mole of lithium equals 6.94 grams. Because we started with grams, we put 6.94 grams on the bottom of the fraction. Grams on the top and bottom cancel each other out. Next, write 1 mole on the top of the fraction. Because the 1 is on the top of the fraction, this becomes a division problem. In your calculator, type 25 divided by 6.94. The answer is 3.6 moles of lithium. You may have been wondering, what happened to the E in mole? Well, it turns out that the abbreviation of mole is MOL. Isn't it just wonderful how much energy we're all going to save by not writing the E? Okay, time for another sample problem. What is the mass of 11.5 moles of lithium? Before we solve this problem, we realized that mass is measured in grams, so we need to convert from moles to grams. The first thing you should do is write down the quantity you know, 11.5 moles of lithium. Next, multiply this by conversion factor fraction. The molar mass of lithium is still the conversion factor. Because we're starting with moles, 1 mole goes on the bottom and 6.94 grams goes on the top. Moles in the top and bottom cancel each other out. Because 1 is on the bottom of the fraction, in your calculator type 11.5 times 6.94. The answer works out to be 79.8 grams of lithium. That is how to convert between moles and grams for elements. But what about molecules and compounds? Let's start by looking at molecules made from carbon, nitrogen, and oxygen. The molar mass of each element is typically written on the bottom. Now, in order to convert between grams and moles for a molecule, we will need to calculate the molar mass of the molecule by adding up the molar masses of all the atoms in the molecule. Let's try a few examples. Carbon monoxide has 1 carbon and 1 oxygen, so we add 12.01 for carbon and 16 for oxygen to get a molar mass of 28.01 grams per mole. In general, the units of molar mass are grams per mole. However, it is very useful to write the molar mass as an equality. 1 mole of carbon monoxide has a mass of 28.01 grams. That helps us remember that the molar mass is a conversion factor. Let's try another molecule. Nitrogen is a diatomic element composed of N2 molecules. Because there are 2 nitrogen atoms per molecule, we multiply 14.01 by 2, so the molar mass of N2 is 28.02 grams per mole. For carbon dioxide, there's 1 carbon and 2 oxygen atoms. So we add 12.01 for carbon and 16 times 2 for the 2 oxygens, which gives us a molar mass of 44.01 grams per mole. We can do the same thing for ionic compounds, like magnesium nitrate. The molar mass of magnesium is 24.3. Because there are 2 nitrates in the formula, that means we have 2 nitrogen atoms and 6 oxygen atoms. So we add 24.3 plus 14.01 times 2 plus 16 times 6, which works out to be a molar mass of 148.3 grams per mole. Remember that we can write the molar mass as an equality. So for magnesium nitrate, 1 mole equals 148.3 grams. That is our conversion factor between grams and moles. So let's go ahead and use this molar mass to do some mole conversion problems. Let's convert 6.35 grams of magnesium nitrate to moles. We will solve this problem in exactly the same way that we converted grams of lithium to moles of lithium. First, write down the quantity that we know, 6.35 grams of magnesium nitrate. Next, multiply this by a conversion factor fraction. The molar mass of magnesium nitrate is our conversion factor. Because we started with grams, write 148.3 grams on the bottom. Because we're solving for moles, write 1 mole on the top. Grams in the top and bottom cancel out. Because the 1 is on the top, in your calculator type 6.35 divided by 148.3. This works out to be 0.0428 moles of magnesium nitrate. What if we wanted to know the mass of 0.369 moles of magnesium nitrate? First, write down the quantity that we know, 0.369 moles of magnesium nitrate. Next, multiply this by a conversion factor fraction, using the molar mass as the conversion factor. Because we are starting with moles, put 1 mole on the bottom, And because we're solving for mass, put 148.3 grams on the top. Moles on the top and bottom cancel each other out. Because the 1 is on the bottom of the fraction, multiply 0.369 times 148.3, which gives us 54.7 grams of magnesium nitrate. Thanks for watching. If this video helped you at all,
Okay,
please
did that
give it
make
a
a
thumbs up.
little
If
more
not,
sense?
Feel free to also
A little more sense once you see it in process. Don't worry, you'll get to practice it a lot. We'll be doing it. It's not too terrible. Remember when we talked about conversion factors a couple weeks ago? And I said, oh, well, when we're doing conversions and it's real simple, like 1 liter over 1,000 milliliters, just write it out anyway, that fraction. This is why. Now on your lab, this is a great example. Everybody has either their lab back in front of them or it was emailed back to them. But on your lab, you take a peek at it. This is where we mean by conversion factor. Is first thing that you did or should have done was get your grams per liter. Here's my copy of it. I put it up. I wrote this out on pretty much everybody's, except I wrote it out with your numbers, whereas this is the numbers I use to make the solution. So if you look at your lab, you'll probably see where I wrote out how you convert your grams per 50 milliliters, which is what you've all started with your solution, to grams per liter. Grams per liter is kind of a standard. You're going to use it a lot, so it helps to have that. All right, so conversion factors, there it is again. We did it just a couple weeks ago. Now we do it again. All right, so in your notes, who has an answer for number? Hold on, well, not important. Number 1. All right, Xander. All right, D. So Avogadro's number is the number of atoms or moles or molecules in 1 mole, which is equal to 6.02 times 10 to the 23rd. All right, how about number 2? Who's got an answer for number 2? Asher.
B.
B, he says. B. Atomic mass, the mass of an atom expressed in atomic mass units. So A, we're looking for A. All right, how about 3? Oh, Gabe. There's your B. All right, there's your B. So that is a mole is the SI base unit used to measure the amount of a substance whose number of particles is the same as the number of atoms in 12 grams of carbon, 12. And a molar mass is obviously going to be C, mass of grams in 1 mole of a substance. All right. What do we get for number 5? Which isotope defines the atomic mass unit, and how is the atomic mass unit defined? What did you get, Jordan?
12 grams of carbon 12.
Right, it's carbon 12, and it's because you've got your 12 grams of carbon 12 is the number of atoms in 12 grams of carbon 12 is a mole, is 6.02 times 10 to the 23rd. So why is a mole used to count atoms? Who's got something for this? CJ?
This is a counting unit.
Yeah. Yeah, there's so many atoms that if you were counting them out, you'd have crazy big numbers. So we just use 1 mole as our conversion factor. That's what we use, our counting unit. Very good. And what's the relationship between an atom's atomic mass and 1 mole of that atom? Who's got this one? Nobody? Jordan?
Moles are the number of atoms, and the atomic mass unit is the weight of it.
Right. So what that ends up being when you're talking about your atomic mass unit and the mole of the atom, it ends up being the same. So atomic mass is molar mass. They're the same. The number will be the same. Okay, how about number 8 in your binder? Atomic mass of lithium is 6.939 AMU. Would you expect the isotope lithium-6 and lithium-7 to be equally common? Why or why not? Which isotope would you expect to be more common? Did anybody hazard a guess here? Okay, so your 7 lithium would be more common because 6.939 is very close to 7. So remember your AMU. How do we get our atomic mass unit? How do we get the number? It's the average mass of all the isotopes, right? So when we're talking about isotopes, some of those are going to be more prevalent than others. So your 6.937 is really close to 7. So if you're getting an average, the number that is going to bring that average closer to 7 is the 6.939. Does that make sense? I mean, but the lithium 7. Does that make close? That I just spoke, I don't even know what. Does that make sense? Okay.
It
So,
does make close.
It does make close there. Okay, so what is the mass in atomic mass units for one fluorine atom? Did anybody have this one? Ooh, CJ.
3.15 times 10, 23 grams.
Okay, so we're looking for 18.998 because that is your AMU. So the mass in atomic mass units of fluorine. So here's fluorine. Were you looking at lithium maybe? Because that's closer to 3. I mean, sorry, not lithium. No, lithium number is 3. So fluorine is right here. 18.998 is its AMU. So that is your mass, basically. So if it asks you what's your mass in atomic mass units, that mass number is going to be your answer. 18.889. I mean, 88998. Gosh, what's happening in my brain? 18.998. All right, what's the mass in grams of one fluorine atom then?
Oh,
Okay, so I think this is where we were going. So here's,
just looked at the wrong.
yeah.
I
All right,
had it up there.
what'd you get?
At 3.16 times 10 to negative 23.
Okay, so here's how we do this. We divide our molar mass by Avogadro's number. So our molar mass is 18.998 grams per mole. When we divide that by Avogadro's number, we get about 8.15. Okay. If you want to write that out or whatever, or make that note, you can. Okay. So, oh, I clicked that early. How many molecules are in 1 mole of carbon dioxide? You got 3 molecules in a mole. Remember, it's a counting number. These are tricky, right? So if you're asking how many molecules are in 1 mole, not how many molecules are in 1 atom, or atoms are in 1 molecule, I think is what you were thinking. How many atoms in 1 molecule? This is how many molecules are in 1 mole. So there's your answer because it's a counting number. So what's the mass of 1 mole of carbon dioxide? Did anybody want to, Colin, did you want to? Hey, okay, now we got one. All right. This is gonna be, I don't expect this to be easy at first because some of this is like, what? So here is carbon, and we're gonna do a bunch of these. So your carbon is 12.011. You have how many carbons? 1. Your oxygen is 15.999. You have how many oxygens? 2. So that's how you get your answer. All right, and we're gonna do a bunch of these, don't worry. So all electromagnetic radiation, including visible light, can be thought of as moving, Hayden, waves or particles. Yep, all right. As the frequency of a wave increases the wavelength, there you go. Frequency up, wavelength down. That was from last year. We did that a lot. So to define the region in which electrons can be found, scientists have assigned 4. Oh, look, lots of people. PJ.
Quantum.
There you go. Quantum numbers to each electron. All right, I'm going to just put these up because I'm watching. Oh, no, we're good for time. Who has number 1? Electromagnetic spectrum is defined as, oh, Lucas. There you go. J, all the frequencies or wavelengths of electromagnetic radiation. Electron configuration is, Colin? E. All right, the arrangement of electrons in an atom. Hold on, I got to make sure I gave you one. And I got to give, where'd it go? Oh, you one. All right. Excited state. What does it want for this? Gabe. C, state in which an atom has more energy than it does in its ground state. Did you excite some atoms today?
Yes.
How'd you do it?
Flame.
Yeah, flame. All right, Asher, what do you get for 4?
B.
B, ground state is the lowest energy state. That's correct. All right, who has Hund's rule? Addie. L states that for an atom in the ground state, the number of unpaired electrons is the maximum possible, and these unpaired electrons have the same spin. All right, line emission spectrum. James. Hey, he says there, spectrum of a few colors seen through a prism when high voltage current is passed through a tube of hydrogen gas at low pressure. Now, you would have seen some spectrum, line emission spectrum, actually with your flame today, had you been successful with your spectroscope, but it looks like most of you weren't. That happens. That's lab. Sometimes it happens. All right, how about orbital? What do we have for orbital? Drew. F, right? Okay, region in an atom where there is a high probability of finding electrons. Number 8, Pauli exclusion principle. Asher. G, states that two particles of a certain class cannot be in the exact same energy state. Quantum number is going to be, Jordan? D. Oh, well, that was out of order.
Wait.
There you go. You're correct. I just clicked the wrong one in the wrong order. D, you're right. Number that specifies the properties of electrons in an atom. Quantum theory. Who's got that one? Caitlin? H. Present day model for the atom. Who was who are the guys responsible for quantum theory?
Heisenberg and
Schrodinger. Very good. Heisenberg and Schrodinger. And your off-bow principle, obviously, is when we haven't done that. I states the structure of each successive element is obtained by adding one proton to the nucleus of the atom and one electron to the lowest orbital that is available. And then your photoelectric effect, which filled early, is what occurs when light strikes a metal and electrons are released. All right. Now, we're going to play.
Hey.
Who's got their phone? You have it? You have it.
Don't have any QR codes.
Oh, your phone should work. If you and just your camera. Put the camera.
It's not Apple.
Oh, I don't know how to do that then. I'm gonna be useless.
No, I can't scan QR codes with the camera.
There's apps to do it.
Yeah, you may want to find an app that does it.
Oh, you said his full name.
Oh, I said part of it. It's much longer. Anybody else have waiting or we got it? We got it? All right. So who is this Avogadro dude? Let's figure this out. Okay, what would you guess is his full name? Come on. Come on. Load. Here it goes. Sometimes it takes it a second. All right, here we go. Carrot, big man. Ooh, Nico Gadro. Emiliana. Edwin. I like Edwin. That's a good one. Dude. I'm a sauce. Avogadro would be an amazing name. I just got to say. That's a real good one. Avogadro. All right, you ready for this one? This dude's name is Lorenzo Romano Amadeo Carlo Avogadro, Count of Caregna and Cerreto. That's fun.
Wow.
You want to see that? Or just his friends just called him Amadeo, because wow, that would be a name. You want that signature? Anybody want to have to write that out every time you sign something? That's fun, right? Wow. Okay. Like nowadays, it's weird if you got two middle names, but this guy had quite a few. And he's a count. All right, so when do you think he lived? We got some date ranges for you here. All right, so y'all are putting in just a little post-Revolutionary War for the most part here. So he was born August 9th, 1776. Hey, we were a country. Just barely. July 9, 1856. So most of y'all got that right. He just missed. This should say TH, and in this font, for some reason, it becomes degrees. Isn't that fun? Just missed his 80th birthday. Just barely. All right, so now where do you live? Spain, Italy, or Tunisia? Tunisia's fun. Where is Tunisia, people? In Africa. All All right, so he lived in Turin, which is at the time Kingdom of Sardinia, which is nowadays Italy. Yeah.
That's not how you spell Italy.
Oh, you're right. Italy. Italy. Oh, you got one, so you have to write it down, right? You got to write it down and put it over there so I can correct it later. What's Turin famous for these days? What? Oh, no. Shroud of Turin. You know that the thing that people claim was Jesus's grave wrapping, right? The cloth that he was wrapped in. They call it Shroud of Turin because that's where they found it years later. Obviously, it's not where it started. Oh, that's a fun one. If you want to go down a rabbit hole about chemistry, carbon dating, and whatever, that's a rabbit hole to go down because it's real interesting. All right, true or false? Was he born into poverty? Okay, is this a wealthy dude? Is this a poor dude? Ah, ooh. We don't know what we think. Remember that name? He was born into nobility. He's a count. Remember that name? Count, blah, 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 blah. So in 1811, he published. Now remember, this dude is Italian, but this is French. So he published something called Essai d'une manière de déterminer les masses relatives des molécules élémentaires des corps et les proportions selon lesquelles et entrant dans ces combinaisons, which translates to what? Molecule in the book is Skibbity Sigma. That's scary. Okay. I'm done. Carrot, carrot, a la carrot. That's good. Grand Book of Carrots and Other Vegetables. Chemistry Book of Madness. I like that. Elementary something. Ah, elementary's in there. Yeah. Book of Short Letters. What the Sigma? A211. Okay. There you go. Somebody looked it up. So, essay on a matter of determining the relative masses of the elementary molecules of bodies and the proportions by which they enter these combinations. Okay, now you see why he's getting this number named after him, because he was trying to determine relative masses of molecules. Aha, dudes in the back, quit the chatter. So what sort of life did he lead? Was he a party animal? Was he pretty well behaved, or was he a recluse? What do we think?
For the people who don't know what recluse is.
Recluse lives by himself like a hermit. Hides away from people.
He's been Kenobi.
What's his name? Shoot, can't remember the guy. Does anybody remember? I believe we talked about her at the beginning of physical science. I think we hit on her again this year. Who was the ultimate party girl? Amélie du Châtelier. Yes, Amélie du Châtelier was the ultimate party girl. Yes, she was.
She's amazing.
Yep, she hung out with Voltaire and got like almost zero credit because she was a woman, but she did all the work. Yeah. So we don't know a whole lot about his life, but it seems he was sober, serious, religious, husband and father of 6 children.
6.
On the note of women not getting any better, Mozart's older sister taught him piano and was better than him at piano. But
There's a lot of that.
talks about her.
There was a lot of that stuff. So I love this one. Take my number. That's an actual etching of our buddy Avogadro. He looks, I'm gonna say this, and it's gonna sound mean, but a lot of those noble families kept their marriages within other noble families. I didn't want to use that word, but their genes didn't get mixed up as much as maybe they should advantageously, and that very small jaw looks questionable to me. So yeah. All right, so
The family of Mobile, Alabama.
you have now. We're going to do more about moles next week. There's a lot more moles coming up and mole conversions coming up. You're going to get real good at it. Okay, so don't worry about them too much. But no, this is your first test aside from your quick, easy Unit 1 test that had one whole lesson based off of it. Now you've got lots of things to study. This is what's on your test. We have a few minutes, so I'm going to go over them a little bit with you. Usually I don't. I throw it up and go, here's your test topics. Good luck. Now, where do you find this if you don't take a picture of it like Asher's doing and y'all in the back are doing? Where would you find this list? Dropbox. On your Dropbox in your resources folder, there's a folder that says Unit 2 Test Study Topics, and that's where you find this. All right, somebody tell me something about reactants and products. Somebody who hasn't said anything yet today. Who hasn't said anything? Rylan and Ridley. All right. Rylan, do you know anything about reactants and products? Anything?
Okay, so the reactants are the atom molecules
Mhm.
that bind to form the reactant.
To form the products, right? So your reactants are what go in, your products are what come out. In a chemical equation, if you were to write it out, where would you find your reactants? On the right or the left? On the left, you've got reactants, yields, products. Good. Physical and chemical changes. Give me something, Ridley. Anything. How do you know a chemical change has taken place?
I just had it in
It's okay. Give me an example of a physical or chemical change. You can do it.
a physical change would be like
That's a chemical change if you've got a color change. So a physical change would be like phase change, maybe? Like ice melting?
Sublimation.
Sublimation, good example. So a chemical change means a new substance has been produced as a product. There's that word, product, produce. You get a new substance and a chemical change. Physical changes, your substance itself does not change. Its phase or state of matter might change. If I crumple up a piece of paper, I didn't even change its state of matter. It's still paper, but it's now crumpled up. It's a physical change. If I burn it, it's a chemical change. If I were to say to you on your test that Jim really wanted a hamburger, cheeseburger. So Jim took the raw hamburger meat and he smushed it all together and he made a patty and he put it on the grill and he cooked it. What type of change did he create?
chemical and
A chemical change because he changed the substance, right? It's no longer raw meat. You've denatured the proteins. That's what happens when you cook it. Physical because he mashed it up. Chemical because he went ahead and put it on the grill and he cooked it. Now he slaps a piece of cheese on top and that melts. What's he got now? A physical change. The cheese is now melty, but it's still cheese. It didn't change. All right, types of mixtures. Your types of mixtures are what? Your main two types. What is it called if it can be easily separated into its constituent parts, like a salad or a Lucky Charms cereal? What kind of a mixture is that?
Homogeneous.
Not homogeneous. What's the other one?
heterogeneous.
Heterogeneous. If you can separate it real easy, like a bowl of Lucky Charms, it's a heterogeneous mixture, right?
Like heterosexual.
Yeah, different. Yes. Now, what is it called? What is it called if it's so well mixed together that you cannot easily separate it? Homogeneous or homogeneous. But it's still a mixture because you can separate it by physical means. Remember the lab with the salts. NaCl, KNO3. Your potassium nitrate, you separate it out by making it very, very what? What'd you do? You decrease the temperature. You got it really, really cold and it crystallized together. So that is how you pulled the KNO3 out of your solution. How did you get the NaCl out of solution? What did you have to do? You had to evaporate the water, which was your solute, so that only your solvent, so that only your solute was left, right? And remember that your homogeneous mixtures include things like solutions, right? Also colloids. What's an example of a colloid? Mayonnaise is a good example. It's the one most people use, right? Yeah, got particles surrounding other particles. All right, phases or states of matter. What is everybody together? Solid to a liquid is melting. Liquid to solid is if I pour metal on the floor and it solidified, melted metal on the floor and it solidified, did it freeze?
No. Yes.
Yes, doesn't matter how cold it is, it still froze. It changed phase. Liquid to gas. Evaporating or vaporizing. Evaporating assumes it's coming off the top, right? Like a puddle. And boiling is all within the mixture everywhere. Vaporizing. Okay, what if it goes from a gas to a liquid? Sublimation. Gas to a liquid?
Condensation.
Condensation. There we go. What is it if it goes from a solid to a gas? And what is it if it goes from a gas to a solid? Deposition. Very good. All right. Now. Basic metric units. We kind of did this earlier. What is our metric unit for length? Meter. Mass? Grams. What about weight? Grams. Yeah. Same. Very good. Volume? Liter. Volume. Right? And what is it for number of particles? Mole. There you go. Yeah. Okay. Know how to do them. King Henry died unusually drinking chocolate milk is what? Kilo? Hecto? There you go. All right, with your unit in the middle. Types of energy. Okay. What types of energy have we talked about? Wasn't physical science, so we didn't talk a whole lot about, what did we talk about? Kinetic energy. What's the measure of the average kinetic energy of a particles within a substance? Nope. Say it. Temperature. That's the next one. Yeah. Temperature is your measure of the average kinetic energy of the particles within a substance. What is heat? Heat is the what? Do you know?
Energy level?
No, it's the transfer of energy. So your average kinetic energy of the particles within a substance is your temperature, and the transfer of that thermal energy is heat. What direction does thermal energy move? Hot to cold or cold to hot?
Hot to cold.
Hot to cold. Why? Think about what you learned today about your electrons. What did they do when you increased their energy? Then what did they do after that? They moved back down, and when they did, they emitted light, because everything wants to be at its lowest energy level. Your electrons want to be at their lowest energy level. You're searching for an equilibrium in the world in general, and that's usually when things are, we're getting into entropy soon, and that addresses this, but yeah. All right, accuracy versus precision. Somebody tell me the difference. All right.
Accuracy is how close you are to the actual thing, and position is how close your measurements are to each other.
That's right. Okay. So when we talk about limits of measurement, this is one that people struggle with on like the first test and whatever. A limit to measurement with you is how precise you are when you're measuring something. Like if all the teams up here all had their triple beam balances nicely calibrated, and I gave everybody a 1 kilogram mass, and I knew it was a 1 kilogram mass, and you all got like, you know, real close, that's going to be how precise you are compared to each other if your measurements are close to each other. But the accuracy is how close you are to the actual measurement. So when we talk about limits to measurement, it's things like the ability of our tools are not completely accurate, right? It's really hard to get something completely accurate. So there's always going to be some limit there, right? And then there's human error too. All right, theory versus law. DJ.
Theory says why, an explanation. Law says what? A fact.
So the scientific law tells you what happens, a fact. The scientific theory tells you why it happens, an explanation. That's one to memorize. Okay, conservation laws. We have mass, matter, and energy, and they all state that what? Colin?
Can't be created or destroyed.
Only changes form. Same with mass, same with matter, same with energy. All right. Endothermic versus exothermic. All right, this was like last week or the week before. Endothermic processes versus exothermic. Tell me.
Endothermic absorbs and exothermic releases.
Correct. And how do endothermic processes feel compared to the environment?
Cold.
Yeah, cold. So exothermic feels warmer compared to the environment around it, because it's releasing energy, typically in the form of thermal energy. Subatomic particles, charges, relative masses. Okay, what are our which atomic, subatomic particles have considerable mass and which does not?
Protons and neutrons are heavy. Electrons are barely.
Yeah, electrons, we don't even count them much, right, when we're doing that. And then your proton has what charge? Positive. Your electron has what charge?
Negative.
Your neutron has what charge? Neutral. Okay. Energy states and levels. All right. This is what we did today with that one, SP. Go back and look at that. Make sure you kind of understand what we're doing. Your main points are everything starts at its lowest state and builds like a ladder, right? Unstable electron configurations versus stable electron configurations. Lowest energy level, and keep in mind the empty bus thing, right? You're going to fill your bus seat. You don't want to sit where somebody else is already sitting. So you fill those first with all up spin, then down spin, all right? Calculating the number of atoms based on volume and molar mass. We just did that, right? So go back and look at that. There may be a question where you have to do that. So we went over all of that today. So you can go back and you can review those. Any question? If your lab is completed, you can turn it in now. If your lab is not completed, you can just hang on to it and bring it back next week. So everybody knows you got a test to do. I'll put these over here on the counter where people can reach in better. People. I think I have a molar conversion. Oh, do you want to go? No, she didn't get them. Yeah.
I got the job.
You did that.
Well, yeah, it's probably because Alex and Bailey works there.
Oh, you're going to the
So,
Brewsters.
so
All
kinda
right.
nepotism. That got me.
Hey, there's nothing wrong with a little nepotism. There really isn't. Well, good. Glad you got it. I was waiting and I didn't get any calls or anything. And I thought, well, I don't know. I hope it works out.
It did.
Well, good. I'm happy for you. That is super news. That is real good news.
Yeah.
Excellent.
Even though I've heard so many complaints from Alex.
I'm sure anybody who works anywhere, you're going to have those. Yes, ma'am. Did you need me?
I was turning in that before.